Hi everyone. Today we are going to perform another example with Nastran Solution 200. The focus of this example is to understand how to use the optimization capability in Nastran to perform what's called model matching or system identification. It might be the case that on one hand you have a finite element model. On the other hand, you've already performed physical experiments on an actual physical prototype. Your goal is then to match the finite element model to the experimental results. So I'll be discussing how to use the optimization capability in the next few moments. My name is Christian Aparicio, and I will be presenting today's topic. So like I said on the previous slide, here is a very simple finite element model. Here in blue are actual experimental results. Here in orange is the first mode of this finite element model. Here in orange is the mode of the finite element model. Here in blue are actual experimental results. You can see that there's a discrepancy. There's a difference between the simulation and the physical test. Our goal is to use the Solution 200 capability to match the finite element model with experimental results. So how are we going to do this? We are going to let the cross-sectional radius of a section of this finite element model, we're going to let this section vary. And by the end of the video, what you are going to find is that our new mode shape here in gray is going to align with the actual experimental results. So we will have achieved model matching by the end of the video. Before I get started, just a quick overview of the agenda. This video can be quite long, so I want to make sure that you understand what we are going to discuss. I'm going to discuss the structural model in a little bit more detail, and then we'll go ahead and discuss the optimization problem statement. In order to perform model matching, what are you going to vary? What is your objective, and what are your constraints? Then, after you define your problem statement, how do you program this for Nastran Solution 200? What's the procedure to convert a BDF file to Solution 200? How do you specify your variables, your objective, and constraints? How do you perform the optimization? How do you then look at the results? And at the very end, how do you update your structural model with the optimized parameters? Now, if you are an engineer, if you're a professional engineer rather, and you are looking for more training, if you have Nastran Solution 200 questions, you're welcome to contact me at this email address, and I would definitely get back to you with an answer. If you're a student or professional engineer and you would like access to the Nastran Solution 200 web app, you can also contact me at this email address with your request, and I will get back to you with a reply. Now let's quickly talk about the structural model. I found this example in the UAI Nastran Users Guide. This example is found in Chapter 25, Section 25.6.6. Now, let me quickly go over how this example is configured. This example is not 100% the same example, but it's very similar. It's a derivation of that same example found in the UAI Users Guide. So here we're using a beam element, I believe, and we're specifying that the beam is a rod cross-section. So the only dimension for this cross-section is the radius. One end is fixed, the other end is free. The length is about 30 units in length. Here's our Young's modulus, our Poisson ratio, and our density. I won't go into too much detail since I believe a lot of us are familiar with those few metrics. Now let me talk about data for the mode shapes. So we're supposing that this very simple fixed and free end rod was experimentally tested. Here in blue, here on the left and here on the right, are what the mode shapes should be for mode 1 and mode 3. Here we see that the Z relative displacement should be about 0.06 here, 0.2, and about 0.6 here for nodes 3, 6, and 9 respectively. We have an idea of what the experimental mode should be for mode 3 for the X relative displacement. Here in orange is what the finite element solution showed. So here, let me exit the PowerPoint and let me open my pre-post processor. Here you can see the first mode shape. If I were to find the values at node 3, 5, and 9, it was in node 6 and 9. This orange line would be this Y line. So this is the mode shape that I found for mode 1. I can also do this for mode 3. Mode 3 is an extension of mode, so you can see it's going in and out. So that's what the orange curves mean. They are the result of the original finite element model. And this is where our problem is. Our problem is that the finite element model is far from actually matching the experimental results. And as I mentioned at the beginning of the presentation, our goal is to use the optimization capability in Nastran to find a configuration of the model that produces the same experimental results. So now let's go over the optimization problem statement. The first design variable will be the radius of the cross section that you see here in the yellow part of the section. This entire rod is actually composed of two sections. Initially, they share the same radius, but we're going to modify the radius for just the beginning section that you see here in yellow. We are going to let the radius vary between 0.1 and 10. Again, the goal is to let the radius vary in the hopes that we can obtain a new structure that has mode shapes that match the experiment. So now let's go over and talk about our objective and constraints. This model is going to produce a number of quantities. It's going to produce natural frequencies. It's going to produce mode shapes. These are the quantities we will be focusing on for this example. So the first quantity we want to focus on is for the objective. Here, what we are going to say is we are going to take the root sum of squares for 3 nodes. We are going to take A to be the difference between the FE solution. So here, I'll say FE solution. We're going to take the difference between the FE solution for displacement or relative displacement and the relative displacement of the experimental solution. So that would be here in blue. So this gap right here is the difference A. So here I've already defined what A is. The FE solution gave me 0.0143 for the relative Z displacement. Here for node 6, the FE model gave me a solution of 0.1741 for the Z relative displacement, and the same can be done for C. Again, think of these as the difference between the FE and the experimental solution here. Then I'm going to take the square root of A squared plus B squared plus C squared. So this is going to be my objective function. Our objective is to minimize this expression here. Generally speaking, we are saying that we want to minimize the error between the FE model and the experimental solution. We're going to perform something very similar for the design constraint. This time, in our previous objective function, we were doing this for mode 1. We want to minimize the error between mode 1 of the FE solution and the experimental results. Here, what we are saying is we want to do the same. We want to express the error for mode 3 between the experiment and the FE solution. But here, instead of saying we want to minimize the error, we are going to say that we want the error to be below 0.002. So we are going to take the difference between the FE model and the experimental results from node 3. So here we have a new expression. This should actually be D. This next value, E, will be the FE solution. So here 0.1 or 0.5431 is the FE solution. Here B2 is our experimental solution. And let me look at this. Oh, I believe I have this in reverse. 0.5431 is the experimental solution, so here I'll write EXP. B2 is the FE solution. So here we are going to take the difference between the two. We are then going to express a root sum of squares expression here. So the square root of d squared plus e squared plus f squared. And then again, I'll talk about how to program this in Nastran Solution 200 in a moment. Oh, I almost forgot. Mode tracking. So we're going to impose our constraint for mode 1 and mode 3. Now, this is very important because the order in which the mode numbers are expressed is in order of increasing natural frequency. So suppose that we apply a constraint to mode 3, which currently has a natural frequency of 263 hertz. If we continue the application of the constraint to mode 3, you'll notice one thing. Mode 3 is now a bending mode shape. Here, mode 3 was previously an extensional mode shape. It went in and out. Mode 3 has actually become mode 4. You can see that mode 4 is also an extensional mode shape. So what we need to do is use what's called mode tracking. This will enable Nastran to follow the mode. So if mode 3 suddenly becomes mode 4, Nastran will be able to track this. If we do not include mode tracking, Nastran will assume that mode 3 will always be mode 3. So if a constraint is applied to an extensional mode shape and then suddenly that same constraint is applied to a flexural or bending mode shape, this can cause issues later down the line. So just to sum up the slide, mode tracking is going to allow Nastran to follow the mode. So the mode goes from 263 hertz, then becomes a different natural frequency. It's going to let Nastran follow the mode and ensure that the constraints are applied to the proper mode shape. Now here's just a quick recap of the optimization problem statement. You can see that our design variables are very simple. It's our objective and our constraints. We've defined error functions, if you will. The objective is to minimize the error for mode shape 1. We want to minimize the error between the experimental results and the FE results. We also define an error function for the constraint for mode shape 3. Here what we are saying is we want to ensure that the error between the experimental and the FE results is within a tolerance of 0.002. So now let's go ahead and go through the process on how to do this for Nastran Solution 200. Let's first start off with the BDF file. This BDF file you may have already produced in your finite element pre-post processor. Here in this example, I'm using Patran. If you want to follow along, let me go ahead and go back and start off in the web app. You can find this starting file in the user's guide. So let's go ahead and open the user's guide. And let's go ahead and go down to this example using MSC Nastran Optimization for model matching. And here for the starting BDF files, click on this link. And then if it doesn't automatically download, you can right click the link and click Save Link As. Let's go ahead and save this to my desktop. So on my desktop is the BDF or DAT file for the same model they see in my pre-post processor. Inside of the BDF file is a collection of the entire finite element model, description of any loading you might have. Here we're performing natural frequency or eigenvalue analysis, so there are no loads, but we have constraints specified. We have the materials specified. Every location of the node is specified here. So this single BDF file is a description of the entire finite element model. So this is our starting point. After you have this file, we are going to use the web app to specify our design variables. We're going to specify our error function for the objective and constraints. We're then going to perform the optimization with Nastran. We're going to review the results. and then we're going to update the original model with the optimized structural parameters that will give us a finite element model that matches the experimental results. So now let's go ahead and start the process. And so here I am on the web app. Click on the size link, and then let's go ahead and select the BDF file we downloaded. Again, this BDF file is a description of this rod, and let's upload it to the web app. Here, let's go ahead and specify or create our first design variable. So for this, search for dimension 1. You'll see that we have two dimensions, one for P bar L1 and P bar L2. If we look back at the PowerPoint, P bar L1 is highlighted here in yellow. So this is what we want to set as a design variable. If you remember, the cross section is circular, and we want to set the radius as the design variable. So let's go ahead and do that right now. So let's click on the plus icon, and here let's ensure we have a bound specified. So here I have that this is allowed to vary between 0.1 units of length and 10 units of length. This completes the creation of our design variable. Let's now focus on creating our objective. Here, you can create your objective as you normally would, but here we're specifying a very specific error function. So let's go ahead and switch to equation objective. This is where I can type in the equation expression I defined earlier in my tutorial. So the first thing we have to do, we have to single out the 3 points of the finite element solution. So here, let me go back. Again, here in error is the FE solution. This is the bending mode shape. I want to single out this value, and this value. So here you can see that the value is about 0.39 here. Here the value is about 0.7. And here I'm just eyeballing it at this point, and this value is about 0.1. So these three values had to be singled out first. So this would be my A1, A2, and A3 terms. So let's go ahead and specify these three terms first. So if you scroll down, there's a section here that's called optional step A. Click on displacement one time. This is going to create a response called A1. I'm going to do this for the third component, or the Z component of relative displacement. This is for mode 1, and this is for grid 3. So what I've gone ahead and specified right now with that one row, I've singled out this one point, this orange point. This is the relative displacement in the Z direction for node 3. I'm going to do this for this point and this point also. So let me step out here and do the same thing. So here we'll create two more responses. This is the Z component of relative displacement, the same mode, but this time this is for node 6 and node 9. So again, I specified these 3 points, node 3, node 6, and node 9. And the reason we are doing this is because these values are going to be used in our expression in a moment. So here A1 is that, A2 is this value, and then A3 is this other value here. And now let's go ahead and type in our expression now. So here we have 0.01483. We're going to take these three values and now type in our expression here. So the square root of 0.0143, which is the experimental result, minus A1 squared, and make sure I close this, plus 0.1741 minus A2 squared plus 0.6381 minus A3 squared, and then close the entire expression. So here let's go ahead and make sure this expression is properly typed in. So here 0.01483 minus A1, 0.0143 minus A1 squared, 0.1741 minus A2 squared, 0.63, see if I can focus this, 0.6381 minus A3 squared, perfect. And again, we want to minimize that this error function. We'll select minimize. Now, we are going to do something very comparable for constraints. This completes the creation of the objective function. Let's go ahead and move on to constraints. So like before, we are going to create one displacement response. This is going to be for the x relative displacement for mode 3, for node 3, and we're going to repeat the process, this time for node 6 and node 9. So let's go ahead and make sure I've done this correctly. So the first component, mode 3, 6, and 9. Okay, perfect. Now we can then create our error function for the constraint. So here we're going to say x, the square root. Let's go ahead and see if I have the constraint defined here. Perfect. So let's go ahead and use this as a reference. Let me zoom in so you see exactly what I'm typing. So 0.1204 minus B1 squared plus 0.5431 minus B2 squared plus 0.9216 minus B3 squared. Make sure I do this correctly, and let me take a second look at my notes just to make sure I've typed in this correctly. 0.5431 B2 squared, 0.9216 minus B3 squared. Okay, everything looks good here. Let's not forget the upper bound. This is a constraint function, so we should always make sure that we have bounds specified for this. Now we can go ahead and move on to the exporter. We'll go ahead and download this new package. We'll extract this package and run Nastran to perform the optimization. So Nastran's running in the background. You see we have the status message. Just to quickly recap, we are going to let the radius of this yellow section vary. We want to minimize the error between the experimental results and the finite element solution. We also want to make sure that the error is minimized, or rather the error is within a tolerance of 0.002 for mode 3. So now let's go ahead and take a look at the results. So here there is a fatal message that was detected. I'm being instructed to open up the F06 file and inspect what possibly went wrong. Here, let's go ahead and confirm that it's the fader. So here we have this error. The gradient of constraint number 1 is 0. Just to save us the time, I will say that I forgot to include a comment, or I forgot to include the mode track that I mentioned earlier. Again, mode track is where you want to ensure Nastran is aware that if mode 3 or any other mode changes the natural frequency and then it's numbered a different mode number, you want to make sure Nastran understands that and applies your constraints accordingly. So here, let me go and open the model.bdf file. So here I've opened it in Notepad. And here, let's go ahead and type in mode track. So mod trak is equal to 800. So this is saying look for mod track entry 800. And then here I'll say mod track with an ID of 800 has values of 1 and 100. And now let's go ahead and start this again. And we'll see if this time we get a successful optimization. So while this is happening, if you do have any questions or comments, my email address is on every slide at the bottom. So feel free to pause the video at any time and send me an email if you have any questions. Here the results were automatically loaded for me. A status page gives me the green message saying hard convergence to an optimum. So that's a successful optimization. The results are automatically uploaded. Here again, the same message, run terminated due to hard convergence at design cycle 4. Here, my error function was minimized. We originally had an error of 0.1978. The error was minimized to approximately 0. And now let's look here and see what happened. Here, the radius started with the value of 2. The radius was minimized and augmented until it found that the best radius to achieve correlation between the finite element solution and the experimental results was, or rather the radius was increased to 3.93. And here, let me just make sure this is the expected solution. Perfect, so it is. So as intended, the optimizer has minimized the error. One thing you might be interested in doing is seeing the actual value for the functions. Here, if you look at normalized constraints, this is not the actual value of the constraint function. So here's a constraint function, so R1. This is not the actual value of R1. This is a normalized constraint value. If you want to actually see what the values for the expressions are, you can go to the results section back in the web app, click on the responses link. If you then upload the F06 file, this will give you a list of all the responses that were taken into account in this optimization. So at the very beginning, I have my A1, A2, and A3 defined here. These three values correspond to these 3 points. So A1 for this point, A2 for this point, and A3 for this point. So that's given here. The same for B1, B2, and B3. This R0 is the value of this error function that we defined earlier. So the square root of A squared plus B squared plus C squared. This next value, R1, is the actual value for this error function here. So R1 square root of D squared plus E squared plus F squared. So this, if you look in the value column, this is the actual value for that error function. This value, 0.1978, this is the actual value for the error function of the objective. Here on the right hand side, you see that we have a normalized constraint value. This value is what's actually used to dictate the optimization. Here you can see the value is 124. We look back at the results. You see at the beginning we have 124. Here we then see it's 41.25. Here it's 3.2. So a shortcut method to view these normalized constraints, you can click on maximum constraint for each design cycle. So here you see that it's 124, 41, and 3.2. So these are the same three that you see here, 124, 41, and 3.2. So there you have it. That's how you go ahead and perform a model matching example with Nastran Solution 200. That's how you go from beginning to end. How do you specify your design variables? How do you specify your error functions? How do you use the web app to configure Nastran to perform this model correlation? Let's see what else is left to cover. We went over the results. Oh, and the solution too. Here is our final solution. In orange was the initial FE solution. So here I'll write init FE. Here in gray is our optimized FE solution. So here, if you remember at the very beginning, the radius was 2. The new radius is now 3.93, I believe. And our original objective was to have finite element solution that correlated to experimental results. So you can see that the gray FE solution is now overlapping the experimental results. And this is for mode 1. Now, if we look at the same thing for mode 3, we see the same thing. In gray is our new FE solution that is overlapping the experimental results. So we've been able to achieve correlation between experiment and the FE solution. Here's just some more data regarding what the new design looks like. You can see the radius has been increased to 3.93. So this is this blue section. And now, how do you update the original BDF file? The original BDF file, if you look closely, the radius is still at a value of 2, but we know the value is a 3.93. What you can do is copy this original file, and here we'll go ahead and call it update it. You can open this file. In the same Nastran working directory, there's a PCH file that's been created. Now, this PCH file has the updated properties for the optimized solutions. So here, if you look carefully, the P-bar L1 entry has a different value for the radius. It's now 3.93. If you look here on the right, the P-bar entry of the old design is still at 2. What you can do here is copy this P-bar L entry. You can replace the old one on the right, and then save the file. And now, this file that's been updated here on my desktop, this has the updated radius that will produce a model that has results that correlate to the experiment. Now, let me see if that's everything I wanted to cover. Yes, it is. Or before that, I'll cover one last thing. You might be interested in seeing the new mode shapes in your pre-post processor. So here it'd be worth me talking about how to do that. In the same working directory where the optimization has been performed, there is a new result file. Here it's an OP2 file. For you, it might be an XDB file. This result file can be brought in to Nastran. So here, let me make sure I'm selecting the correct file. This result file will now have 2 sets of data. Here you see we have data for mode 1 and then a second set of data for mode 1. If you scroll to the right, you see these markers that say D0 and D4. D0 corresponds to the results of the initial design. That's what D0 stands for. D4 stands for the results of the last design cycle. So here you can see that the last design cycle was design cycle 4, which was a final solution. So these results with D4 are the new optimized structural results. So here, if I plot that, you can see that the interior of the mode shape is actually a lot less than it was before. So these results, if you were to go ahead and plot this on the spreadsheet, will be the results that are in gray. So these gray results, this mode shape for D4 that you see here, these will actually be overlapping with the experimental results. So just to sum up the last 2 minutes of discussion, the result file includes results for the initial and the optimized design. You can bring in this result file to your post processor and you can view the optimized structural results, otherwise known as the final results. That was the last thing I wanted to cover. Again, if you are a professional engineer and you would like to ask me a question, I would be more than glad to help you with an answer. If you're a student or professional engineer, you can get access to the Nastran Solution 200 web app. You can contact me at this email address and I will also get back to you. With that, I'll go ahead and stop here and thank you for watching.